here's going to be a short video because I already did out this homework problem, but here's the solution to homework 2, problems 1 and 2. I already worked it out. I'm just going to narrate through the solution. So here's the problem. It's another door handle. It's slightly more complicated, so you have to kind of like visualize what this thing looks like in 3 different views. And I gave you 750 newtons coming down this way in the FX, 300 coming downwards in FY, and 400 going in this Z direction. All of them are in the negative direction for their axes, and the dimensions of this are 200 millimeters in this direction, right? 200 millimeters is about 8 inches, right? You can think of that 25 millimeters per inch, right? Or 25.4 really, but you could just kind of round it if you're trying to visualize. So this thing's like 8 inches long, 4 inches high because it's 100 millimeters in B, and C is 75, so about 3 inches coming this way, and then E is like 50 millimeters, right? And then I usually reserve D for the diameter. So the diameter of this is 20 millimeters, around 3/4 of an inch. Actually, 19 millimeters is really close to 3/4 of an inch. Just if you're ever using sockets and wrenches, you could know that you could actually use a 19 millimeter. Anyway, I digress. Actually, yeah, okay. All right, so here we go. This is homework 2, and I really do want you to write out the problem. Now, I know this one has a little bit of drafting to it right there, but that's really sort of the problem. It really does help you think your way through the problem, and I suggest you use a straight edge, and you kind of use the 30 degrees each way right there for our isometric. And if you take like parallel lines as you shift really through it, like you can take that parallel line and you can see that goes up to there and up to there. And this kind of exercise, writing out the thing very carefully in engineering paper, is really going to pay off. So I would really strongly encourage you to do that. But also in terms of documentation, this is a great idea. Okay, so we want to find the stresses on element B, which is on the side. So our first thing maybe I'll go ahead and figure out the loads. So I start off with my free body diagram in the, let's go to right there. The free body diagram in the XY plane. And I notice over here, by the way, I point out that this is actually not needed. And you go, well, why is that? Because we're looking for the stresses at B. The stresses here, or the bending moment here, I should say, is going to get you stresses that will be on the top and the bottom, whereas B is right here in the center. That's the neutral axis of this, right? So this moment doesn't cause any stresses at B. It's actually going to be about the y-axis that's going to cause a bending stress at B. So this was just for completeness and kind of just going through the routine. So you could have saved yourself a little bit by not doing this. We go to the next view right here, and so this is the XZ plane, and see that Y is coming out of the page, and we're looking down onto the thing, right? So we're looking down, and this is a really good exercise to do to see what that would look like in the XZ position. Now here we go. And in these first 2, I went ahead and found what the reactions were in the X and Y, and then I do it now in the Z. Now the truth is, we could just from observation just pick these out because there's only one force in each of these directions. So this is just to kind of reinforce that we should be kind of methodical about our approach to the thing, and try to be neat about it, right? Okay, so now we take the moment about Y, which isn't going to be important to us, and we do find that there's a competition between the loads. You can see that the 400 newtons is going counterclockwise, and we're going to multiply that by 200 millimeters, or just 0.2 right there, so we can get into Newton meters. And then the 750 is going clockwise. And we could see that that's going to be multiplied by the 75 millimeters right here. So when I went ahead and chose as the default as counterclockwise, And so based on that right there, I find out that this is actually negative, and therefore it was in fact clockwise, right? But if I don't know, and this is the case where I don't know because I have these two competing against each other and I'm not quite sure who's going to win out between the two, it turns out this guy wins right here, right? He's larger than the magnitude of this, so this ends up being a clockwise moment reaction, and I get 23.75 Newton meters. All right, and then now I need to have the ZY plane, or the YZ plane, and that's looking down this long axis, looking down in that direction right there. So we're going to see this kind of shape here, and then that's going into the page. So we see this right here, and it's really important. Well, we do recognize, it's important to recognize that this moment right here is going to be the torque, right? It's going to be the torsion is going to happen onto there. So I just went ahead and called that T. It is the reaction in the about the x-axis, but because that's the long axis, that ends up being the torque. And here too, we have a competition between this 400 newtons wants to go clockwise, 300 wants to go counterclockwise. But so by default, I chose it as positive reaction, and it turns out it was a positive reaction. So yay for that. All right, so now that we have those loads, I think it's a good idea to summarize this in a stump. Now, recall, let's just take a look at the one that didn't matter, right? The one that didn't matter was that 52.5 about the Z right there. But in here, we knew that it was going to be clockwise. So here it has to be counterclockwise, right? Because these, when we're cutting these off as a free body diagram right here, this is cut. We're looking inside this piece. So we're finding this reaction internally, but then there's got an equal and opposite for the stump, right? So the thing was cut off as a free body diagram. What was left is the stump, and so with inside right there we have equal and opposite, right? So that was clockwise, that ends up being counterclockwise. Similarly, we have this is going to be counterclockwise because we found this to be clockwise, right? And they're equal and opposites, and we're cut it inside the thing. And then lastly, we see that this one is going to be clockwise because this was counterclockwise. And when it comes to the reaction forces, noteworthy, this was down, this was over to the right, and this was into the page if we were looking out right through there. All of these forces, they just transfer from here over to there. Now they're going to be these are going to be the opposite of what's inside the reactions right in there. Like you see, this is the reaction that's on to this face. Well, it's equal and opposite onto this face because we've cut the two. Right? I think I hammered that home. All right. Now we do some geometry. I could have done this first, but I just get the area, moment of inertia, and polar moment of inertia right there. Now we start to go to stresses. And our first stress that's going to be on B is going to be on axial, and it's going to be compression. So it's caused by this guy right here because he's right down the axis and he's pushing there and he's squishing it, so it's got to be compression. We go to the next one. As we mentioned before, it's the 23.75 right here that's causing a stress at B, and it's going to be tension. Now you could see, because it's coming this way, that it's going to be pulling on that. It's going to be pushing on this side, right? So that thing is pushing onto there. You could also have done it off of this guy right here, right? You can, okay, now, so we have to remember that this is going to be opposite, right? So it's actually in this direction. We could revise this drawing, but then this would be true, right? So I'm going to keep this drawing the way it is. But remember that it is actually coming in this direction, right there. And this is where B is. So even from here, you could see that it's causing a tension pulling onto there, right? And now we come down to torsion. right? So we'll talk about direction here in a second, but we know that this is the 37.5. And so R, which is the same thing as is just the radius, right? 1 over the diameter, which is 20 millimeters. So it's 0.01 is what R ends up being, and divided by the polar moment of inertia right up here. And then our last stress that's on this is the transverse. That's the hardest to remember most of the time. We'll note that we want to go to the force. This is 300 because it's the transverse is maximum at the sides to each side. It's 0 where it passes through. So you might mistakenly want to choose 400, but it's going to be 0. 400 creates 0 where it's passing through the thing. 400 would actually create maximum shear up here and down there. So that's to remember. Now we want to look at the direct. We know for the when we're going to sum this up, that's compression and that's tension. We want to these are going to counteract each other, right? So this is going to reduce some of this. We're going to subtract that from here when we get to the force. Now okay, so like here's me combining the two things right there, right? So here we see that that's subtracted out, so that's what the overall X stress is going to be. Now this one, it takes a little more thought. The torsion. Let's take a look at the torsion from up here. It's going to be this is the cube we're looking at. It's going to be coming up the face. You can see how that's rolling around this way. So it's going to the torque is going upwards if this thing is in the XY plane, which it is, right? So the torque is going to go up the face, right? But then you see this transverse, it's going down the face, right? Because it's cause of this right here. So that goes down the face over there. So you can kind of picture those, torsion coming upwards across the face, transverse coming down. And we subtract that out. So that's what the total shear is going to be. And then we summarize it on a stress element, making sure that we have these arrows. These got to point towards each other, and these have to point towards each other. So that's like problem 1. I try to go through that relatively slowly. I will post this video and you can work through those them yourself. Okay, so here we have principal stresses, and I'm looking at the clock. I have 20 minutes till class, so I might want to just try to go a little bit faster in there. For the principal stresses in this problem right here, we have positive, so there's tension. There's going to be negative, so that's compression, and then we have 20 clockwise. So let's take a look at that. How I went about that. I drew that on a stress element. Then I took this face right here and I plotted that point 35 and 20. And then I took this face right here, which is 10, but a compression. So that's over here in the negative side. And this is counterclockwise, so it's in the lower part. Right. This one was clockwise, so it goes to the upper part of our tau, right? I should probably have labeled these too, by the way. Tau, sigma, right? So I drew a line between them. I find the center of them, right? So it's the average of them, and it gives us like 12.5. And then I need the radius. So this one right here was easier to take as the radius. So I went ahead and found the X leg of this is really just going to be this stress minus C to get that leg right there. So they have the 35 minus 12.5, which I've just found. And then we get the rise, which is 20 right there. And so that's the radius. To get the first principal stress that I'm calling sigma A, I add the center and the radius together, and that's my answer. For the next one, for B, I subtract the radius from the center, and of course I get a negative value, which I anticipated by way of my more circle. And then I can summarize, noting that the maximum shear up here is equal to the radius, right? There's the radius there, but it's also equal to this. So there you go. There's the solution. Here is the second problem. I went ahead and did pretty much the same routine. In this case, we have tension and tension, and then this one's counterclockwise. So it looks like this right here, tension and tension, and then that's counterclockwise right there. So that's the one that I'm referring to most often. There's that right-hand face. And then here I do the same thing. I take the average and I get, well, okay, first off, I plot the points. So I plotted this face that ends up being down here, and then I plot this face, which ends up being right there. And then I find the average, 35.00. I think that's a 0. That looks like a 6, doesn't it? And then I find the radius, and that's going to be easiest if instead now I take the center and I subtract out this, what I'm calling sigma y right there. So that's going to get this leg, and then of course plus the square of this. So now I have the radius, and for principal stress A, C plus R, principal stress B is C minus R. These are both positive numbers, they end up being tension. So right here is the answer. Now this next problem is a difficult one, but we do it over and over again, so we want to make sure that we master it. All right, so we have, let's see, I'll go look at this right here. Here is the problem where we have pulleys, and we're given these forces, but we're not given these. So this is 120, and this is 25. This thing is at a 45-degree angle. The distance here is 12, 16, and 8. And the diameter here is 3/4 of an inch. That's pretty big. And then the diameter of this pulley is 8 inches, and the diameter of this pulley is 12. So I drew out the thing. Didn't make it exactly looking the same there, but I communicated it pretty well, I think. Looks decent, right? And we want to find the maximum bending stress and the torsional shear. We also know that the loose side of this is 25% of the tight side. So I did the geometry first. We don't need that area, but I went ahead and did it anyway. Now my first load that I want to try to get, I want to find these unknowns. And just from observation, seeing that this one is more than that one. So I drew the free body diagram with everything intact, right? So I'm looking down the x-axis here. So everything is intact. And I take some of them. Well, first off, before you even do that, I can see this one is more than that one. Therefore, and so this has a tendency to make it counterclockwise. So this one needs to be more than that one to go clockwise, to counterbalance the thing, right? So I can write out that statement right there that they said that the loose one is 25% of the tight one, right? There you go. And then I take my sum of the moments about the x, and I'm able to, I put in this FB1 here, right? And we can see we have positive and negative for each of these things. And then I put in for FB2, I just substitute this relation, and I'm able to solve for FB1. And then FB2, of course, obviously once I knew FB1, I could put it back into there. Now I need to do this whole thing again, but now I want to do it with the shaft cut, and maybe I shouldn't have made it that cross-hatched right there, right? So the shaft is cut, and I take the sum of the moments and balance it out. So this is the torque that's inside the shaft that is resisting these pulleys right here, and I find that it's 380. And I also, while I'm here, I decided that I wanted to find what the total force is going to be between these two combined in the Z and the Y direction, because I'm about to use that over onto the next thing right there. Okay, so now I take and I make two diagrams of my original problem. Right here's the original problem, and I look at that view of the XY, and then I look at that view right there of the XZ. and I have it all laid out with my dimensions, and you can see that here's part of that force from the 45 degrees, and here's the other part from that force in the 45 degrees. And there's nothing on this one in this view, but there is entirely, when we're looking down upon it, the combination of both the of this force and that force, those combined are all in the z direction. So I go ahead and do my statics on this, right? So sum of the moment, do it about O. It's a good place to start. Do it about here first, and then I'm able to get what this reaction is. And we can see that both of them are going down because that's the only load that's going onto there. And then with that, I can get what the reaction, when the sum of the forces in the y direction, able to get the reaction in the y direction there. So I have both of those reactions. I do the same thing over here. Take the sum of the moments about this point right here, and I'm able to get this reaction. Then I take the sum of the forces in the z direction, and I get this other one now. Notably, this force is going that direction, this force is going that direction. So the reaction here, this one's pushing down against that, and this one's pushing up against there. Sometimes we can't have it where one of the magnitudes is so large that actually one of the reactions that's close to there will go in the same direction. It's like a teeter-totter effect. It just matters what these distances are and the magnitudes, so just be in the wild. But anyway, so we have this kind of situation here where for our shear moment diagrams, which I'll just briefly mention, where we have this reaction coming down. So we start at that reaction, and then we place this force onto it. So we add that to it, right? So that was negative, and then we add this to it. And we come along, and this value right here, once we added this to there, this better be equal to this reaction. Because as it comes along over here, when we come to that, it needs to come back to 0. And then to get the moment of this, we just take the area of this. So that's just 68.33 times 12. And we get this, and actually that technically should probably be negative right there, right? And then this is, we get up to this value, and then it's going to come down and go to 0. As an easy way of finding this value, all we need to do is take and find this area right there, and that's going to give us this value. In a similar way, we had this reaction coming downwards of 44.87. We get to this point over here, and we add that, or actually subtract it, because this is the negative direction, z is in that way. And then we come over here, and boom, this force comes downwards, and we end up getting 47.97, which we should have got from statics anyway, but we can confirm it. And then we find the area right here, get it right to there. Easiest way to find this one is to go from this direction instead and find the area of this. So that's going to come up to here. And then you can see that it crosses right there. There might be some situation where we might want to find this, but we don't need to do that right there. And so we want to get the magnitudes of these moments. So we get A and A together, right? Because this is both in the same spot on the shaft. And we get this magnitude right here of the total moment. And we do the same thing for this point and this point. And we find this is the most, so the most bending occurs right here at A. So we want to find the stresses at those places. So we take that and we do the MC over I, and we get 23.69 KSI. And for the shear, we take the TR over J. And we're going to neglect transverse shear in this one. So the only two types of stresses in this are going to be a bending, normal stress, and a torsional shear. And then here's the answer. So there you go. It was a long and involved explanation, but certainly is going to be shorter than me writing it all out. Hopefully this was helpful. And so we'll hit done.